Deepen Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello everyone. In our previous class, we have started with the chapter Haloalkanes and Haloarenes. In that, we have seen the definition of haloalkane and haloarenes, nomenclature, how to write the IUPAC names, and then we have studied the methods of preparation. Under the methods of preparation, first method was from alcohols, second one from hydrocarbon. Under the hydrocarbon, three methods of preparations were there. First one by free radical halogenation, second one by electrophilic substitution reaction, and third one from alkene. Under the alkene, we have studied two reactions. One was addition of hydrogen halide and the second one was addition of halogen. Then we have seen the physical properties. Under the physical properties, we have seen melting point and boiling point for same alkyl group, for isomeric alkyl halide and for isomeric dihaloarenes. Second property was density and the third property was the solubility. After that, we have seen the chemical reactions of nucleophilic substitution reaction. So, when alkyl halide was treated with the cyanide KCN, we got alkyl cyanide. If it is treated with silver cyanide, we have got alkyl isocyanide. Same way, when alkyl halide was treated with potassium nitride, we have got alkyl nitride. And if alkyl halide treated with silver nitride, we will get nitroalkane. Okay. Now, let us move on to the nucleophilic substitution reaction. Before that, we will just see the stereochemical aspects of nucleophilic substitution reaction. Certain compounds rotate the plane polarized light through the polarimeter when it is passed through the solution. Those compounds are known as optically active compounds. And if the compound does not rotate the plane polarized light, it is known as the optically inactive compound. Now, optically active compound, if the light rotates towards the right hand side, it is known as the dextrorotatory and it is denoted by small d or plus sign, positive sign is put before the degree of rotation. If the light rotates towards the left hand side, it is known as the levorotatory and it is denoted by small n or negative sign. Dextrorotatory, it is a Greek word. Dexter means towards the right hand side and levios means it is towards the left hand side. Next, we have the asymmetric carbon. What do you mean by asymmetric carbon? The carbon which contains the different atoms or groups attached to it, that carbon is known as the asymmetric carbon. So, if you look at this carbon contains the different atoms or groups attached to that. So, that is known as the asymmetric carbon. Now, we are going to learn the two terms, that is the chiral and achiral. If you take left hand and mirror image of that will look our right hand, and if we try to place the mirror image, it is not going to coincide. For example, this way, if we take our left hand and see in the mirror, it will look like a right hand. So, if we place it on one another, it will not coincide. So, that is known as the non-superimposable mirror images. So, same way it is shown. But if you take the bottle and if you see the mirror image, though it will look the same and it will coincide with that and it is superimposed. So, non-superimposable mirror images are known as the chiral and non-superimposable are known as the achiral. Let us take an example. Now, if I take an alphabet P and draw the mirror image of that, it will look like this. So, if I place the P letter on this, it will not coincide. So, this is known as the chiral. Second alphabet, if I take A and draw the mirror image of that, it will look like this. So, if I place this on this, it will coincide with that, and that is known as the achiral, and that process is known as the achirality. Non-superimposable mirror images are also known as the enantiomers. If you consider this molecule, if X is replaced by Y, here the structure remains the same, only the replacement of X will take place with the Y. We are getting retention. The structure retains its identity. If you take X and replace that again with the Y, but you can see this is just opposite way. This looks like the mirror image of that. So, that is known as the inversion. Invert means opposite. And if I get A plus B, that is known as the racemic mixture, or that process is known as the racemization. In racemic mixture, if we get 50% of the mixture, the degree of rotation will get cancelled. It will have the 0 degree of rotation. That is because we get the rotation is through the right hand side and the rotation is through the left hand side. So, therefore, it will get cancelled and we get the racemic mixture, and that compound will be optically inactive compound. We will see the two types of substitution, nucleophilic substitution reaction. The first one is substitution nucleophilic bimolecular, that is also known as SN2 reaction. Now, let us consider the reaction. Alkyl halide, that is the methyl bromide, when treated with the hydroxyl ion, will get methanol plus Br minus. As you all have seen in the chemical kinetics chapter, how to write the rate of a reaction. Rate depends upon, rate is directly proportional to concentration of the reactant, and when we remove that proportionality sign, we include the proportionality constant. Okay. So, here two reactants are there, therefore, rate of a reaction depends upon concentration of both the reactant. Now, if we want to find out the order of a reaction, so order will be here 1 concentration, so that is raised to the power 1, and 1 molecule we are using, so raised to the power 1. What is order of a reaction? The sum of the powers raised to the concentration terms, correct? So, this is 1 plus 1, so the order of reaction is 2, therefore, it follows second order kinetics. Now, we will see the mechanism of SN2 reaction. If we look at the mechanism, the incoming nucleophile OH minus attacks on the carbon, and the leaving group, that is the old bond, will start cleaving or cleavage takes place. So, this process occurs simultaneously. So, in the transition state, no intermediate is formed. Here the new bond will form between the carbon and the nucleophile, and the old bond will start breaking. So, since this stage occurs simultaneously, that is known as the transition state. If you look at the reactant and if you look at the product, we are getting the structure is in an opposite way. We are getting inversion of the configuration gets opposite. So, this is known as the inversion of configuration. In this we are getting inversion because OH attacks on the opposite side and the old bond will get break. Okay. So, this is the mechanism of the SN2 reaction. Now, let us look at the reactivity of alkyl halide towards SN2 reaction. Methyl halide primary alkyl halide, secondary alkyl halide and tertiary alkyl halide. If we consider, when we compare the methyl halide with the primary alkyl halide, this hydrogen and this hydrogen is same, this hydrogen and this hydrogen is same. But if you look at this hydrogen and here it is a methyl group. So, the molecular mass of methyl group will be more. So, when we compare these two structures, this one will be considered as the heavy group or the bulky group which is present. Okay. So, if the bulky group is present, the steric hindrance increases, and if the steric hindrance increases, reactivity decreases. Now, when we if we compare the primary and secondary, that time in secondary 2 bulky groups are present. In tertiary 3 bulky groups are present. So, when the nucleophile attacks on this, more the number of alkyl group or heavy groups or bulky groups are present, nucleophile attacks becomes difficult. So, the steric hindrance increases and reactivity decreases. Now, when we compare these 3, so the order of reactivity will be methyl halide, primary alkyl halide, secondary alkyl halide and tertiary alkyl halide. So, methyl halide will be more reactive as compared with the primary, then secondary and the tertiary. That means, tertiary alkyl halide are least reactive because of the presence of 3 bulky group and maximum steric hindrance. So, this is the reactivity of alkyl halide. Now, based on this, the question may come that the questions or the compounds will be given. So, you have to arrange or you have to identify which one undergoes SN1 or which one undergoes SN2. Okay. Second one, now we are going to see the second reaction, that is substitution nucleophilic unimolecular. Now, to write the rate of a reaction, rate depends upon the concentration of the reactant. So, in this SN1 reaction, rate of the reaction depends on only one of the reactant. Though we have the 2 reactant present, the rate of a reaction depends upon only one of the reactant. Why it depends only one of the reactant? That we are going to see in the mechanism. Now, if we want to find out the order of a reaction, so this one will have the first order, only one reactant, so it will be having the first order kinetics, and therefore it is known as the unimolecular. Now, let us see the mechanism of SN1 reaction. Step 1, formation of carbocation. Formation of carbocation takes place when we take the third butyl bromide. This is the slow reaction, and slow reaction is the rate determining reaction. Here the heterolytic fission takes place and the bond will cleave between the carbon and the halogen, and the electrons will be taken up by the electronegative, that is the halogen. So, the formation of the carbocation takes place. Now, since it is the rate determining step, and as we have studied in the chemical kinetic, Rate determining, based on the rate determining step, we can write the rate of a reaction, and according to that we can find out the order of a reaction. So, if you look at the first step, only one of the reactant is involved in the reaction, therefore, the rate depends upon the only one of the reactant. Okay. Step 2, this is the same one, the carbocation. So, carbocation, on that the nucleophilic attack takes place, that the nucleophile attack. Now, nucleophile can attack on the carbocation from the same side also, and it can attack from the opposite side also. Okay. As we have seen the formation of the racemic mixture, in this case we are going to get the 50-50% of mixture, and that is known as the racemic mixture, because the nucleophile attacks from the same side and it is also attacking from the opposite side. So, two mixtures will get, and that is known as the racemic mixture. So, this is about the SN1 mechanism. Same way we are going to see the reactivity of alkyl halide. Since tertiary carbocation are stable, the reactivity of tertiary halides are more. So, the order of reactivity in case of SN1 reaction is tertiary alkyl halide, secondary alkyl halide, primary alkyl halide and methyl halide. It is just opposite to the SN2 reaction. Chemical properties of haloalkane, under that first reaction we have seen nucleophilic substitution reaction. Now, the second reaction is elimination reaction. Elimination reaction, it is also known as the beta elimination or dehydrohalogenation. Elimination, that means we have to remove something. Now, what we are supposed to remove? D means removal, hydrogen, halogen. So, that means we have to remove hydrogen and halogen. Now, let us consider an example. If we consider an alkyl halide, the halogen which is attached to the carbon, first carbon, that carbon is known as the alpha carbon. The next one is the beta carbon and the next is the gamma carbon. Now, we are going to focus mainly on the alpha and beta carbon. Since we have to remove the hydrogen and halogen from beta carbon, we are going to remove one of the hydrogen, and from the alpha carbon the halogen will go. Okay. That means, in this reaction we are removing hydrogen also and halogen also. So, that is known as the dehydrohalogenation, and the formation of an alkene takes place. CH3 will remain same as CH3. This hydrogen we have removed, so here the CH will remain same. Single bond will get converted to the double bond, and this is CH2. This is the name of the reactant is 1-bromopropane or N-propyl bromide, and this one is prop-1-ene or propene. So, when we start with an alkyl halide in presence of alcoholic KOH, we are going to get an alkene plus KBr plus H2O. K plus OH minus, this one is the Br minus. So, it will combine with the K plus, so we are getting KBr. OH minus, we are also removing the hydrogen, and hydrogen carries the positive charge. So, that will combine with this and we are getting the H2O. Now, let us consider one more example. The name of the reactant is 2-bromobutane. As I have said, first we have to consider or identify the alpha carbon. Since the halogen is attached to this first carbon, so that is the alpha carbon. The next to that is a beta carbon. On this side also we have the adjacent carbon is known as the beta carbon. So, we have in this case 2 beta carbon. Number of beta carbon, number of products we are going to get. That means, in this case we are going to get the 2 products. Now, we will consider the 2 path, that is first we will consider as beta 1 and beta 2. So, what we can do? We can split this hydrogen so that we can show the easy removal of the hydrogen, since it is an elimination reaction. Now, this is our beta 1. So, we have to remove one of the hydrogen, any one of the hydrogen can be removed from the beta carbon. So, if we remove this hydrogen, this halogen will go, that means dehydrohalogenation takes place. So, we will write the first product from that beta 1. So, what is left over here? CH2 single bond will get converted to the double bond CH, this CH2 and CH3. The name of the compound is but1ene. Now, we will follow the second one, that is the beta 2. So, this part will remain same. So, when we follow the beta 2 carbon, now we are going to remove any one of the 2 hydrogens are present on the beta carbon, we can remove any one of the hydrogen. So, let us remove this hydrogen. So, this halogen will be removed, again dehydrohalogenation takes place. Now, whatever it is left we have to write. So, this part will remain same, CH3, this is CH. Now, the bond, double bond is going to form here. So, that is double bond CH, CH3. So, the product is but2ene. But2ene is the major product. Now, how to identify which one is the major product? That depends upon the Setzeff rule. According to the Setzeff rule, it states that greater the number of alkyl groups are present across the double bond, major is the product. So, it is, if it is more alkylated, major group is that. So, now if you look at over here, across the double bond, in this case 2 alkyl groups are present. If you consider this, across the double bond 1 alkyl group is present irrespective of number of carbon atom. Okay? So, 2 alkyl group, therefore, this one is considered as the major product and this one is considered as the minor product. So, this will be in the 80% around and this will be around 20%. Okay? That is the elimination or dehydrohalogenation. You can try with the different examples also. Now, the third reaction that is left is reaction with metals. Alkyl halide, when treated with magnesium in presence of dry ether, we get RMgX, that is known as the Grignard reagent. Grignard reagent, when further treated with water, we get an alkane. So, this reaction can be considered as one of the method of preparation of an alkane. We can try the different example. R we can replace with CH3, X we can replace with ClBr. Okay. If I take R as methyl group, so the reaction will become CH3Cl plus Mg in presence of triether CH3 MgCl, that is methyl magnesium chloride will be formed, and methyl magnesium chloride when treated with water will get an alkane along with the byproduct. The alkane form is known as the methane. Under the reaction with the metal, this is the first reaction. Second one we have, that is very familiar and we have already studied that, the Wurtz reaction. So, again here when we consider the two molecules of an alkyl halide and treat that with the sodium metal in presence of the ether, again we are going to end with an alkane plus 2NaX. Now, I am always telling my students also, when we write this, if this reaction is given in this way, you have to split in right, so that it will be easy for you all to show the removal. Now, the same reaction I will write two molecules we are taking. So, one molecule I have written Rx and the other molecule I will write it in an opposite way in presence of ether. Now, here we can show the easy removal, that is we can remove 2NaX. So, write that 2NaX. Now, what is left? R and R is left. So, that is our main product. Okay. Now, we will consider one example for this, that is very important. This is an example with 2-idopropane. So, we have to take 2-idopropane and we have to carry out the Wurtz reaction. So, we have to just do the rearrangement of this. So, if I take that CH3 here and I over here, that is one and the same thing, that is the 2-idopropane only. So, to show the easy removal of the halogen, we have to write in this way. So, treat that with the sodium metal. Now, the same reactant, because we are taking two molecules of that. So, the same we are taking in a opposite way. So, it will be ICH CH3 CH3. Show the removal and write whatever it is left. CH3 CH CH3 is left. So, that I will write first CH3 CH CH3. This we are going to remove. This is going to get joined, that is CH CH3 CH3 plus 2 NaI, because many times the students make mistake while writing this reaction. So, the name of the product is 2,3 dimethyl butane. So, that is the Wurtz reaction. We have seen the reactions of haloalkanes. Now, we are going to see the reactions of haloarenes. Again, it is divided into three First one is the nucleophilic substitution reaction, second one electrophilic substitution reaction, and third one reaction with metals. Now, if you look at aryl halides are extremely less reactive towards the nucleophilic substitution reaction due to the following reason. The first one is the resonance effect. If you look at the resonance effect, the electron pair on halogen atoms are in conjugation with the pi electrons, and these are the structures. So, we are getting on ortho position electron rich center, para position electron rich center, and again on the ortho position electron rich center. So, these are the resonance structures of chlorobenzene. Okay. In this, the carbon chlorine bond acquires double bond character, and double bond character due to the resonance. As a result of that, bond cleavage is difficult, therefore, the aryl halides are less reactive. Second one, difference in hybridization of carbon atom in carbon halogen bond. In case of haloarenes, the halogen atom is attached to the carbon, and that carbon is sp2 hybridized. This is what we have seen in the classification. And if you take haloalkane, the halogen atom is attached to sp3 hybridized carbon atom. sp2 hybridized carbon is having more s character and is more electronegative, therefore, the bond length gets shortened in this case and the cleavage becomes difficult. This is the second reason, that is why the aryl halides are less reactive. And the third reason is formation of the phenyl cation. Phenyl cation, that is the instability of the phenyl cation. Phenyl cation undergoes self ionization and that will not be stabilized by the resonance. So, these are the three reasons, that is why the aryl halides or haloarenes are less reactive towards the nucleophilic substitution reaction. So, these are some of the replacement by hydroxyl group reaction with the haloarenes. Now, if we take the chlorobenzene and treat that with the NaOH at 623 Kelvin and 300 atmosphere pressure in presence of dilute HCl, the Cl group will get replaced with the OH. So, chlorobenzene will get converted to the phenol, that is one of the method of preparation of phenol. Second one, the nitro group on the para position. So, para nitrochlorobenzene if we take and treat that with NaOH at 443 Kelvin, again the Cl will get replaced with the OH, that is the para nitrophenol formation takes place. The third reaction is 2,4 dinitrochlorobenzene when treated with NaOH at 368 Kelvin, again in the presence of dilute HCl, will get 2,4 dinitrophenol. And the last one is 2,4,6 trinitrochlorobenzene when treated with water and we just warm it. So, we get 2,4,6 trinitrophenol or picric acid. This is the picric acid which we have used in the lab to carry out the potassium test. Second one, first one was the nucleophilic substitution reaction. Second one is electrophilic substitution reaction. Now, just now we have seen the resonance structures of the halobenzene. Halogens are highly deactivating group because of their strong negative inductive effect. Therefore, overall electron density on the benzene ring decreases. However, due to the resonance, ortho and para directing groups or positions are more stable. Now, we will see the electrophilic substitution reaction. Under this, we have the 5. First one is halogenation. In halogenation, we use FeCl3 as a Lewis acid and that will act as a catalyst. So, chloronium ion attack on the ortho position and the para position, as we have seen that in the resonance structure, because ortho and para positions are the electron rich center. So, the electrophile attacks on that centers. So, we will get 1,2 dichlorobenzene and 1,4 dichlorobenzene. In this, para product is the major product. Second reaction is nitration. In nitration, we use the nitrating mixture, that is concentrated nitric acid and concentrated sulfuric acid. Here the nitronium ion act as an electrophile and that nitronium ion will attack on the electron rich center, that is on the ortho position and also on the para position. In this case, we are adding the concentrated sulfuric acid. So, in nitration, the concentrated sulfuric acid act as a catalyst only to increase the speed of the reaction, and we will get the 1-chloro-2-nitrobenzene and 1-chloro-4-nitrobenzene. Third one is sulfonation. So, in sulfonation, we will get 2-chloro-benzene sulfonic acid and 4-chloro-benzene sulfonic acid, and the para product is the major product. The fourth one is Friedel-Crafts reaction. Under the Friedel-Crafts reaction, we have two types. One is the Friedel-Crafts alkylation and second one is the Friedel-Crafts acylation. Now, chlorobenzene, when treated with the alkyl halide, any alkyl halide you can take, or even we can write as Rx also. So, here I have taken the methyl chloride in presence of anhydrous AlCl3 that act as a Lewis acid. We will get the 1-chloro-2-methylbenzene and 1-chloro-4-methylbenzene. Second one, when we take the ethanol chloride, that is an acetyl chloride, the bond will get cleaved over here and this one will have the positive charge. So, this will come and attack on the ortho position and on para position. So, the compound will get the ortho directing and the para directing. The name of this compound is 2-chloroacetophenone and 4-chloroacetophenone. So, these are the 5 reaction comes under the electrophilic substitution reaction. Now, under the Friedel-Crafts, one is known as alkylation because we are adding alkyl group, and the second one is known as the acylation because we are taking the acyl chloride or acyl halide. In all the 5 electrophilic substitution reaction, we get para product as the major product, and the last reaction of chemical reaction of haloarene is reactions with metals. First one is Fitic reaction. Fitic reaction is similar to the Woods reaction. Woods reaction is carried out for an aliphatic alkyl halide, whereas the Fitic reaction is for the aryl halide. Now, if we take haloarene and treat that with the sodium metal in presence of dry ether, so same way I have shown the removal of 2NaX and we will get the 2-benzene, that is a phenyl ring, that is known as the diphenyl or the biphenyl. And second reaction under that is the Woods Fitic reaction. Woods reaction is for alkyl halide and this is for the aromatic. So, we will take, anyhow we are taking the two molecule. So, one molecule of an alkyl halide will take and one molecule from the phytic, that is aryl halide. Same way we have to show the removal. So, R is our alkyl group. We can replace alkyl group with either methyl, ethyl and so on. So, that is the one molecule from the Woods and one molecule from the phytic we have taken. So, that is known as the Woods phytic reaction. So, today we have seen in this chapter chemical reactions of haloalkanes and haloarenes. Under the chemical reactions of haloalkanes, we have seen nucleophilic substitution reaction. Under the nucleophilic substitution reaction, we have studied SN1 reaction along with the mechanism and reactivity of alkyl halide towards the SN1 and SN2, and we have studied the nucleophilic substitution bimolecular and unimolecular reaction. Second one we have seen elimination reaction, that is also known as the dehydrohalogenation, and third one was the reaction with metals. In reaction with metals, we have studied formation of the Grignard reagent, and when Grignard reagent was treated with the water molecule, we got an alkane, and the second reaction was the Woods reaction. Under the chemical reactions of haloarenes, we have studied three reactions, that was nucleophilic substitution reaction, second one was electrophilic substitution reaction. Under the electrophilic substitution reaction, we have seen 5 reactions: halogenation, nitration, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation, and last one was the reaction with the metal, that is first one is the phytic and second one is the Woods phytic reaction. Now, you can see this video on YouTube or Prudent Media. Thank you.
Prudent Scholars, powered by Lupin Pharmaceuticals.